Great, we can get started. Thanks everyone for joining today. Today we have Zhiwan from, well, as of most recently UCLA, but she'll be moving to Los Alamos very soon. She did her undergrad at Fudan and has been on STAR since about 2019, I think, where she mostly focused on CME searches in the VPS2 data set. And I believe that's what she'll tell us about today. Just also wanted to highlight that she recently won the Sharp Goldhaber Prize and gave a great talk as part of the acceptance for that. So I'm sure it'll be great. So please, whenever you're ready, go ahead.
Thank you, Esther. Hello, everyone. I have introduced myself. I'm Zhiwan. So it's actually it's a pleasure to be here and introduce you to some of the latest findings at STAR about the effect. I understand that most of you guys are focusing on the jet structures. And then, so I hope that I can do a good introduction to let you know what we are trying to look for right now in terms of this, we call it a novel QCD phenomenon, the chiral magnetic effect. And then, so I will divide my talk into several subsets. I will first do some introductions to the idea, what are we trying to look for and what it means in our experiment. And then I will focus on the latest developments of the new methods that developed, also the mechanisms with the STAR Event scanning data. And then I will summarize this problem. So let's start with the elementary particles. I think for modern physics, what we try to focus on is what's the basic entities of the matter. And about 2000 years ago, we developed the idea of the first truly evidence was discovered in late 19th century by biologists. It's called the Brownian notion. And then later on in the early 20th century, Rutherford discovered that the atom is called the nucleus, and the nucleus are made of protons and neutrons. But about 50 years ago, people find that the protons have particles inside. Later on, they name it as quarks. And here becomes so far, to our knowledge, the basic entities of matter for now. But can we divide it further, into strings and something else? That would be an open question. That's why I put a question mark here. It's actually for our generation to discover that part. And also, when we talk about elementary particles, what we really interest is what kind of physics it carries. For this talk, we are focusing on the parity. So what is parity? We can divide those particles based on their spin and the momentum direction into left-handed and right-handed particles. When we try to observe them inside a mirror, the left-handed and right-handed, they switch their position. This symmetry is called the parity symmetry. And when we talk about those particles as the massless limit, this handedness of matter is sometimes called chirality. So that's how we came up with the chirality. That's the first word in chiral magnetic. You can get knowledge to that. And then parity symmetry, as well as a fundamental symmetry, is not always conserved. For example, the parity symmetry is violated in the weak interactions. As you know, we have 4 basic interactions. However, there's something spectacular about the weak force. That is, the weak force only acts on left-handed particles, which means if we do an experiment in 1956, it was the cobalt-60 experiment. And then they discovered a symmetry of beta rays, like up and down. So this is kind of a discovery for the parity symmetry breaking in the weak interaction. This leads to the Nobel Prize in the second year for the theorists Young and Lee that proposed the idea of parity violation in weak interaction. And then for chiral magnetic effect, we are trying to observe something that's similar but in the strong interactions. You probably will ask, since strong interaction can act on both left and right-hand side particles, where does the parity violation come from? It actually comes from the intrinsic properties of QCD. So one of them is that it's what we call the asymptotic freedom. This leads to the fact that QCD vacuum is not empty. Instead, it's full of energetic gluons. And on the other hand, another property is called confinement. And we know that at high temperature, for example, those temperatures reached by RHIC and RHIC, the confinement of a proton and neutron, they break down and you have liberated quarks and gluons. So on the middle, I show a famous QCD phase diagram. On the y-axis is the baryon density, and on the x-axis is the temperature. In our high-energy experiments, what we are trying to do is to collide 2 hadrons, but at nearly speed of light, to create a phase transition into a new phase called quark plasma. And this kind of phase transition is very similar. If you think about it, it's very similar when we try to change the water into vapor by increasing the temperature to a higher extent. So this is our relativistic heavy-ion collider. It's on the Long Island in Europe, 2 hours driving from here. It's 2.4 kilometers in diameter. And if you look at it, there are 2 current active experiments. One is the STAR. STAR has been running for nearly 20 years, more than 20 years. And then the other one is Phoenix. Phoenix just went online last year. So altogether, there are 2 running experiments. At RHIC, we can collide like various particles down to proton up to uranium. And for us, the most let's say species that we collide at across different energies is the gold on gold species. So if we take a look at a typical gold on gold collision, notice that it can be divided into 2 parts. In the middle, in the between, is a typical like non-central head-on collisions. We have those nucleons called participants. They create the quark plasma at the center, where you have quarks liberated and also excited gluons. Those excited gluons can help us to probe the PCB vacuum. And then on the edge of the nucleon, where you have those protons just fly away at the speed of light, they actually also create something very important to this study. That is because they carry positive charge, the symmetric protons on each side, they create a strong magnetic field at the center. And then with the strong magnetic field, with the liberated quarks and those excited gluons, you will see like how these physics come up together and then help us to manifest the intrinsic properties of systems. So before that, let's talk about our STAR detector. It's located at 6 o'clock of the RHIC. It's called the solenoid tracker of RHIC. And then it's a complex like a system with very different small detectors. At center, it's the projection chamber. It's like a can like right here in our beam line. And it has different forward and backward detector systems. So I like circle out 2 of the STAR detectors that are most relevant to this work. And then on the right-hand side is the front and side view of the first gold-to-gold collisions at STAR. It was taken in 2013. When we actually take a look at the time evolution of the heavy-ion collision, we notice that it is very similar to the Big Bang theory happened at early universe. If we first concentrate on the right figure, when the 2 Lorentz contracted nuclei, they hit each other and create the fireball. And later on, it like experienced some very complicated dynamics where you can see jet comes in and then you have hydrogen gas and you have all kinds of gamma like radiated. And in the end, they become like the particle tracks that can be detected by our time projection chamber and all the other detectors. And this process is actually quite similar to the Big Bang. So sometimes people call it the small bang at RHIC. And then because they are similar, it allows us to study some kind of physics that happen at early universe through the heavy-ion collision. For this, I want to introduce this the baryogenesis. So we know that baryogenesis explains like why we have more matter over the antimatter, and it happens at very, very early universe, about microseconds after the Big Bang. So in our heavy-ion collision, of course, we cannot reach that high temperature. So instead, we study a similar physics to the baryogenesis. We call it chirogenesis. It means it generates more left-hand particles than the right-hand particles, or vice versa, inside the local domain. So how do we understand the similarity between these? We need to go back into the details and focus on the topological properties. That's what we call the non-perturbative part of our group theory. So if we take a look at the PCB vacuum, it actually has some intrinsic fact that first, it's not empty, as I explained. The chiral condensate is average. And also the vacuum, it has a specific topology structure, as I showed in this plot. So how to understand this? You will notice that they have different values, and these different values can be considered as a vacuum. So they are like quantum states, but they are superposition of like each other, that altogether they are the so-called QC vacuum. If we assume like there is an angle between the superposition, what we call theta QCD, then we can rewrite this vacuum into a simple subset. And this theta can contribute to the effective Lagrangian term. Sometimes if you really work on the astronomy physics, this theta is called the strong CP violation problem here. And from the recent measurement, this is very small. So why this fine tuning is there? Because there's no reason it's not there, and there's no reason it's there. People actually studying on this. For us, what we are interested is if we can probe like different topological sectors in our experiment. The good thing is, I forgot to introduce here. So you notice that this is a different value. You name it with a number n. That's the Chern-Simons number in or in other words, that's a topological number. And then if it's 0, it means we have equal number of left and right-hand particle. If it's smaller than 0, we have more right-hand particle. If it's larger than 0, we have more left-hand particle. And then the good thing is that the energy barrier, the height, in other words, of this vacuum is around like 100 MeV. And if we record the temperature that we can have right now in LHC and at RHIC, it's around like 150 MeV, something like that. So that's the good part, which means we are able to probe it with the energetic gluons. So how do we do that? It's from this equation. Like if you have a gluon field and it's energetic, you can actually change like through these two like topological values. That's called the NCS, or sorry, delta NCS. That means you can jump between them through the semi-classical like equation called Sepharad. Or if you have constant tunnel, that's called the axiom. So there are different possible ways. And then when we actually study this in our QCD, we realize that since electroweak vacuum, it's SU2, it's a subset of SU3. So actually it has very similar substructures, except one thing, that the energy barrier height is very high. It's, if you compare it to our QCD energy barrier, it's around like 100,000 higher, which means we definitely cannot reach that right now in our current energy. But instead, this may happen in the early universe. And when we talk about the change of the delta NCS, the topological number in the electroweak vacuum, what we notice is that it will change a number of electron plus baryon. That means it explains why we have more baryon, more matter than antimatter in early universe. Of course, this is one explanation for the baryogenesis. There are many others. So that means if we can really probe this PCD vacuum, it can help us to understand the electric weak vacuum. So that's one side of it. But as I talked about, this thing is an intrinsic PCD property. So how can we like manifest it in our observation? This requires another condition. That's the strongest magnetic field. Actually, those spectator protons, when they fly away and create a magnetic field, they do have some imprint on our PGP matter. So this is a recent publication. If we take a right-hand side notice, is that we are trying to measure the charge asymmetry as a function of the centrality, charge asymmetry of the V1 cell. So the expectation is if there's only quark effect, it's insensitive to the centralities. It's like the black line here is quite flat. But if there's magnetic field increases when you go to more peripheral collision simply because you have more proton, right? And then you will see a monotonically decreasing. So these two effects combined together, what you will observe is a rise and down this non-monotonic trends in the asymmetry of the V1 cell. And that's exactly what people saw with the proton, like the red data point right there at 200. So that is the evidence of the magnetic field imprint on matter. And then if we now come to our like main role here, that's the chiral magnetic effect. What does it mean is, assuming we have a little bubble. So this is our little bubble here. It's a local bubble, the topological bubble, where we can use those excited gluons to create a place where you have, in this case, more right-handed particles. And then since right-handed particles and left-handed particles, their spin are like anti-parallel. And then depending on their charge, they will choose, when you turn on the magnetic field, your spin will either align with magnetic field or anti-align with magnetic field. So in this way, you will create a charge separation at the top and at the bottom of the bubble. So this is what we call the magnetic field induced charge separation for quarks that's current imbalance, or CME, the chiral magnetic field. So this is actually quite interesting because when you write down the equation here, it's very simple. On the left-hand side is the charge separation or the current J. On the right-hand side is your magnetic field B, and there is the mu phi. And then if you assume locally this mu phi is non-zero, left and right hand, so you have different parity. So that's what they call the local parity violation. If we measure the ferromagnetic effect. It's very similar for charge parity, but I didn't write it down here. It's a homework vector to you guys. It's very easy to figure out. So if we take a closer look at the three conditions of CME, the first two, parasymetry restoration and topological vacuum transition, it has to be there because it's the property of PCD at high temperature. What about the strong magnetic field? That is the key condition because we don't know if this magnetic field can coexist with the previous two. That is the reason that we want to do a beam energy scan, because when you lower your energies, the magnetic field lifetime might change. You can consider like if I travel a little bit slower, the magnetic field will decay a little bit slower. We will come to that part. So here is a lot of equations, but that basically is trying to argue how do we observe this charge separation. Some of you might be familiar with this Fourier expansion, but some of you are not. So what we do is we take the particle azimuthal angle and then write it down with respect to the so-called reaction plan. That's our XZ plan. And then the first Fourier coefficients before the sign term, that's called A1. It's proportional to the size of CME. However, because it's a quantum fluctuation, it can either go left-hand side or right-hand side. The average value of A1 is 0. What we measure is the variation of A1, or A1 squared. So that's a parity even value sensitive to charge separation. This is the CME charge separation. But that's not the end of the story because we have charge separation from other effects. For example, here we show a picture of the non-CME charge separation. Assuming we have a resonance particle, a rho, and then it would decay into like positive negative charge ions, right? And assuming this rho is like a floral, the elliptic flow distribution. In other words, if there are more rho's going on around the reaction plane, then you will fake the charge separation signal. That's what we call the background charge separation signal. So if we then take a look at the common CME observables, gamma correlator, R correlator, sign balance functions, they are similar. They have similar sensitivity to both signal and to the background from a recent STAR publication. So here we focus on this gamma observable. And when we write it out, you will see it contains the A1 squared fluctuation term, also a large B2 related background. So the part is when we try to cancel the V1 related background, we can subtract the same sign pair in gamma from opposite sign pair in gamma, just as when we do a lot of combinatorial background calculation to reconstruct the signals. And then this means the CME signal is that when delta gamma is positive. However, those background mechanism, it will also produce a delta gamma that's positive. So if our measured charge separation signal is from CME or from other backgrounds, we don't know here. That requires us to put a lot of effort into how to mitigate the background. So on the other hand, we have a similar background indicator. The only difference is we change the coefficients here from 1, 2 to 1, 3 plus 2. This background indicator, it has very similar backgrounds happen in the CME. I'm sorry, in the semi-observable delta gamma. So now let's come to the early CME measurements. Here we have the results from Alice and from the STAR Event Plane data. It was published in 2014, so around 10 years ago. And then the first thing we realize is that the opposite sign is indeed above the same sign. So like the blue data points is above the red data points at different energies from 2.76 TeV down to the 7.7. So then, does it mean that we have the CME charge separation? No, because we know it has a background from a flow-related and a non-flow-related background. To estimate the background, there is a rough estimation. What we can do is we can compare this normalized observable kappa. Idea is you assume CME, everything comes from the flow-related background. So you can like divide your delta gamma with that value V2, and it's coupled to some like local chart, to some two particle correlators called delta delta. And then you can compare this kappa from your data with the pure background model. That background model we currently use AMPT. The first thing you notice is that at the highest energy, at least energy, and at the 7.7 GeV of RHIC energy, the two are consistent. So, and then in the middle, you do see some deviations. It seems to indicate that at very low beam energy, the chiral symmetry is breaking because there's no difference between data and model. On the other hand, at very high energies, so at this bigger point here, you see maybe there is no deviation of the net. Why do we like, so we don't know, that's why we put a question mark here. Why do we argue kind of things like that? Because if we count the magnetic field in vacuum, that's what I showed here. The orange one that's rapidly decay, it's calculated at RHIC. And then the gray band here is like assumption when we have the quark plasma, the QGP around 0.1. So, and then you can see that at RHIC energy, the magnetic field probably already decayed. While like at other like lower energies, the lifetime of the magnetic field could be longer. So, however, there's one thing to notice is that the gray band shown with AMPT, although we see some deviation, we cannot argue that we do see some like non-trivial things because AMPT model could be underestimate the background. So how to really deal with the background? Here comes something serious. This is known as the isobar equations. It's a major DOE project that the data was taken in the year 2018 and 2019. So the idea is that since we cannot directly mitigate the background so easily, just do the experiment twice. It's called a control experiment. One using ruthenium and ruthenium, the other using zirconium and zirconium. What's the difference between those two species? They have very similar, they have the same like atomic number, 96, but they have different number of protons. So in other words, their backgrounds are very close. So if we compare their backgrounds, they're almost the same. But when we compare the size of the magnetic field, ruthenium has 4 more protons, right? So the magnetic field would be stronger. Then if we do the double ratio for ruthenium over zirconium, we expect larger than 1 for the CME picture or equal to 1 for the pure background picture. That's our assumption. And then at that time, we assume if we have 2.5 billion events per species, the uncertainties will be beat down to 0.4%. In other words, with the fraction of CME in our observable is larger than 14%, the difference will be larger than 2%. It's like 14% times the difference in the magnetic field. And then it will yield a 5 sigma significance. So that's our assumption. That means the discovery. And then for these isobar equations, we did a very strict blind analysis for 5 groups. UCLA is one of the major group. And then the results of isobar is quite striking because instead of finding something above 1 or equal to 1, we find something below 1. So there must be something like wrong. I will put it like a quote here, something that's going on here. And instead, if we compare these data points with the purple line here, it's 1 over our multiplicity. We notice that the multiplicity is actually not as unity. So the multiplicity is a little bit higher in ruthenium than in zirconium. After isobar blind analysis is published, we did a post-blind analysis. We try to match the multiplicity exact, and then what we find is the different observables give the value that's consistent with 1. So it basically tells us that the signal fraction of our FCME in isobar is quite small. And then for a smaller system, it will be background dominated, as the simulation shows here. So you will see that it's very small, but the black dot is gold on gold, and then those overmarkers of isobar is only like twice the size of gold. So a smaller system would be background dominated, and it's a double for FCME. So I was like, I just passed my ATC around this time. And then at that time, we want to pick up a thesis project. And then we want to like ask what's the lesson that we learned from isobar. So the first is we can't just let the background contribution go away. We really need to dig into that. We need to investigate that background contribution. And on the other hand, we should go back to larger collision systems. So go again, become our favorite like collision system. So how to mitigate the flow-related background? There has been an early attempt. These are results from Alice and CMS group at RHIC. What they use is the event shape engineering. I put a traditional mark here because later on we will introduce a new method that was improved from this. And then what they do is that they use 3 sub-events at different rapidity. One for the event of particle of interest, one for the event plan, that's a proxy of our reaction plan of the charge separation, and then one for the event shape variable Q. It's the module of the flow vector. So Q is defined by its X and Y value here. Then we can measure the delta gamma versus Q, V2 versus Q. Everything is being by this value. So you have a bunch of like data points here, and then do a linear fitting to extrapolate the 0 V2 intercept. What both Alice and CMS they observe is that the intercept at 0 flow background is like consistent with 0. It seems to indicate that there's no CME or there's no deviation of the magnetic field. However, there is a caveat of this method is that you notice the first data point is so away from the true 0. So when you do this linear extrapolation, it's quite a long shot and it's unstable. We investigated further with the simulation. It's a viscous fluid dynamic model invented by those theory guys working on CME, and it's targeted for this analysis. So we can switch on our like the signal level, N5 over S, you can think of it as the signal level, from 0 to background, to moderate signal, to strong signal, and then use a second order polynomial compared with the linear shot to evaluate the systematic uncertainty. Then what do we notice is that this method works if the signal is quite large. So here you will note there are 2 data sets. One is the blue markers. They are the observables. And then we have our true input signal that's are marked by the red markers, the A1 squared, the variation of A1. And then you will see that they meet at the zero flow value here. So it means 0 flow background here. So it really works when there is very large CME signal, but when you go to true background case, how to say that, like the uncertainties, the systematic uncertainties is quite large. So how to improve that method becomes our task. And then to understand that, we need to go deeper into the idea of event shape. So what is event shape? It's the shape of specific events. And then if you take it out event by event, you will notice, even if we start from the same eccentricity, when you try to measure the final particle distribution, it could be spherical, could have different shapes. This is called a large event by event or emission pattern fluctuation. And what really contributes to the CME signal is both the emission pattern fluctuation and this eccentricity of participant zone geometry. So then it means in order to work on that, we should use the particle of interest because it is sensitive to both sources. So this is the idea of event shape variables built on the particle of interest. And I have to note, CME background comes from the combined combination of these 2. So then you will ask, what happens if I just go straight to use the particle of interest as my selection? So there I listed here that would be our first option, scenario A, that's using the single particle Q to beaming our events, and then use our use our single particle V2 in the x-axis. So it turns out that this would be problematic because using the same kind of particle in Q and V2, you are actually missing something very important, what we call residue background. This is a very simple scenario. You have a rho meson decay along the x-axis and into 2 pions, pi plus and pi minus. For here, we notice that the V2 of pions we measure is 0, but the V2 of rho here is not 0. That is the picture of resonance. flowing resonance decay. And you measure delta gamma, you have it's positive, it's called the pure background case. So when you try to use the simple Q square to measure it, it's still 0. In other words, you are missing this kind of resonant background. So instead, what we come up is, because it's a decay, right? Why don't we just use the decay to reconstruct to the what we call the pair E2. But instead of focusing on a specific decay channel, we use the inclusive decay channel. So everything added up together. And this comes up with our pair E2. So as you notice, we can use single particle or pure particle to construct our Q, and then single particle, pure particle to construct our elliptic flow. So we have 2 times 2, 4 combinations. And then using the same kind of particle still will give some under subtraction of the background. So those mixed recipes are favored. In addition, when we expand this Q correlator, we notice it's not exactly at 1. You have to use higher order normalization. That's why we redefine our Q square with a extra normalization. So let's see how it works. So we actually first test this method with different models. This is the ABFD simulation results. So you can see scenario A, B, scenario C, and D. Those are 4 different methods. And similarly, we try to plot delta gamma as a function of V2. V2 is our background. We try to extrapolate it to the 0 background limit. And then we can compare our observable to the true signal to see if those 2 intercept matches. When we switch from the traditional method to this new method, the first thing we notice is now our data point, the first one, is very close to 0. And this ensures that our extrapolation is more stable. And then when you compare this, what we call statistic uncertainties in our intercept, it was beat down by a factor of 5. So this is one of the advantages. And when we compare these 2 values, we do notice that in scenario A and B, the intercept is higher, which means resonant background exists. When we switch to the mixed combinations, that means when we divided the events into subsets using pair Q, but measure everything like delta gamma versus single V2 or vice versa, and then this residue background is suppressed. So in scenario C, it turns out to be our optimal case because they actually match it pretty well. We also test it at a pure background scenario. This is moderate signal level, 0.1. We test it at 0, pure background, and 0.2 strong signal. It turns out this method is very robust. It is always can reproduce the true signal in the movement. And also, you will notice that this predicts an ordering pair to compare those intercepts of traffic. It's A larger than B, larger than B, larger than B. And then we test it with a different model, ANPT, and we notice even the first one is very well suppressing the background, and it seems to overestimate the background, while with the same ordering. Then we take a deeper look into this ANPT model. We realize that the backgrounds, like charge separation background, could come from majorly 3 sources. One is the resonance decay, another is the local charge conservation, and then also the transverse momentum conservation. ANPT does pretty well in the transverse momentum conservation, but when it comes to the local charge conservation, it's not tuned to data. In other words, ANPT cannot describe that part of background well. It's probably the reason that we get this over subtraction here. So this shows this is how our analysis details how we proceed. The first, we categorize it with a higher order normalization flow vector. So the flow vector distribution actually looks like this. And then we measure everything with respect to this specific event. In other words, we measure V2 to this Q2 value, delta gamma to this Q2 value, and then take out bin by bin the data points to point them on the Y and X axis. So here we have 2 plots. On the left-hand side is our CME observable, delta gamma. On the right-hand side is a background observable. This is used as a verification of the method to see if it can give us back the 0 intercept for a pure background case. And then after we obtain this intercept, it requires a small correction. This is the idea of non-interdependent flow, but I will not go into details about that. And then this becomes our delta gamma restored value. So we can compare this value to the inclusive delta gamma that contains background to see how this method works. And then with the newly developed method, we really want to work on complete analysis. So this is the beam energy scan at RHIC. Here, the x-axis is the center of mass energy. The y-axis here is our different kind of collision system. As you can see, I circle out the beam energy ranges from 7.7 to 27 GeV. And then also we have a lot of 200 GeV data set here. So then we can do a full systematic evaluation of the belt. For beam energy scan, we have our phase 2 just to finish the data production and the quality assurance. So you will see a lot of beam energy scan results in the near future. And then for these, the first thing is we have 10 to 20 times higher statistics. It allows to do precision measurement. Also, in 2018, we have the detector upgraded. This EPD detector turns out to be crucial because it has a specific coverage observability that's target the spectator region. So EPD is a scintillator detector. Whenever you have a charged particle hits on the tile, it can record the value. And then, as you can notice, EPD is divided into different tiles. The inner tile of that, it can track the spectator. So this is the ULQMD simulation. And we have 2 EPDs, east and west, located in the forward and backward direction. With those symmetric, we can also suppress the momentum conservation background. So with these 2, it allows us to reconstruct the spectator plan. In other words, we can know our direction of magnetic field. So now we have applied our method to the data analysis to go at 19.6 GeV. And then if we now write down our observable delta gamma, it contains 3 contributions: the signal part that we are trying to figure out, and then the background part from the flow background and non-flow background. Non-flow can be suppressed by the spectator side wave constructed from EPD. Also, we have our latest developed method, eventually selection, to suppress the B2-related background. And then now we are interested to see how the signal portion, how much does it yield in the final. So we again apply this ABCD result. The 4 recipes here, I have to remind you, we have, I'll go into details again. And then we will focus on this C scenario, as from the model simulation, it can accurately reproduce the signal input. So the ordering of the y-intercept, it actually follows the prediction from both ADFD and AMPT. And then after that, if we take a look at this bottom corner on the left-hand side, we notice the intercept is actually not 0. It's a little bit finite, to sigma finite, at 30 to 40% of centrality. Now, what we can do is we can repeat it at different centralities. So for CME, we want both magnetic field and proton plasma as the prerequisite. That means our sweet zone would be between 20 to 50 centrality level. Because at the most central, you have QTP, but there's no magnetic field. And at most peripheral, you have magnetic field, but there's no QTP. So in other words, we are going to focus on the big central collisions. So after we applied to different centralities on left upper corner, this is our gamma 112, the semi-observable. Here is the background indicator, and this is the ratio, like when we divided this to the value without any background subtraction, this can tell us what's the fraction of CME observable. And then first, the ordering of the 4 intercept, it follows both models. So we are going to focus on the scenario state here. And then when we do a fit into our sweet zone in the syntology for 20 to 50, we notice that after B2 background subtraction, we find a finite signal in the mid-centrality events. This is about 3.3 sigma level, including the systematics. And then for the background indicator, delta gamma 132, those green values, after we combine it, it's consistently 0. And if we take a look at the ratio, it's around 16% plus minus 5. So this is a really good sign. Then we repeated this for several other energies, 227, 19, 14, 11, 10.2, and 11. The first upper row here is the CME observable. The lower row here is the background indicator. So the background indicator is consistent with 0 at all energies. This gives us some confidence that this method works in terms of subtracting the background. And then if we focus on here, we see a rise and fall trend. So the peak is around 19, 14, and 11 GeV, around 10 to 20 GeV. And then at 200 GeV, it's consistent with 0. We didn't observe any charge separation signal. Also at like the other energy and the lower energy at 9 and 7 it also later seems to favor the 0 CME scenario. But in the between, for those 3 energies, we observe a finite signal, like finite significance, 3 sigma for each. Here is when we try to now plot everything as a function of energy dependence. So if you take a look closer, this is the result before any background subtraction as a comparison. And then the blue data points, the blue circles here are the CME charge separation observable. And then the green values here is the delta gamma 132, that's our background indicator. So the background indicator is consistent with 0 everywhere. And then from the CME observable, from the ratio, we notice the highest value is around like 20%. That means at least 80% that comes from the background. Also, we don't forget this energy data point on the right-hand side. This is at 200 GeV. What we have, the ratio is -2 ± 5 ± 2%. And then this gives an upper limit about 10% total. Remember that the upper limit of SCME is like half of in the isobar than gold because gold has more like protons than the isobars that they come with, which means it has larger magnetic field. So it is equivalent to about 5% in the isobar. That means we will only be able to see 0.7 difference if there is CME in isobar at 20, and it's too small to detect. We don't have that much statistics. So this seems to be like help us understand why we didn't observe it isobar. On the other hand, if we do a literal combination for those 3 data points, each with 3 sigma, we will reach a over 5 sigma significance. This is assuming the similar physics condition between 10 to 20 dB. And so far, we are still working on how to understand that part. So this is from the experiment side. Also, the lower energy part, it seems to break down, but from other measurements on the elliptic flow and the QGP related relation, people still believe that there is QGP at 7 GeV. Then how to understand that the ESS result approaches 0 at these two? Does it indicate something like the chiral symmetry restoration and QGP might be split in the magnetic field? Also, we also compare our results to a previous indicator. This is a revisit to the B- scan 1. In B- scan 1, the H correlator is introduced. The idea is if we take a look at here, we directly subtract the V2 background from delta. And then, but there is a prior here, kappa. So we don't know kappa. It's an unknown parameter, and we can compare kappa equals to 1, 2, 3, whatever. You can compare those lines. In BS1, what they observe is a rise and fall trend. Now, with the BS2 data, we can calculate this kappa observable based on the results. When kappa is set to 2.5, we see that those gray data points, the H correlator, it matches pretty well with the delta gamma correlator from ESS results. So the flow background can be reasonably well described by an universal coupling. And this is also quite interesting. So now I would like to talk about some outlook because we notice a rise and fall trend, and that is not the only measurement in this energy region, 10 to 30 GeV. For example, when we take a look at the V1 slope that is sensitive to the equational state, when we take a look at net proton, the first panel is antiproton, the second is proton, and then when we subtract the antiproton from proton, we have the net proton. And then we notice that this slope is the smallest in between the 10 to 30 GeV, and it becomes negative. So it is indication of is there a first order phase transition near this region? Also from our recent STAR net proton cumulate measurement. So the idea is the first order phase transition would predict a non-monotonic trend, like a deviation from your model that where they use hydro gas and URPMD model, and then you will see a non-monotonic pattern for the C4 over C2 hyperons. And then they also noticed that there is a 4 sigma deviation near 19 G, and also between 10 to 30 G, you will see a significant deviation from pure model. So near critical point region, the topological fluctuation will be enhanced. The reason is very simple. Near critical point region, your QGP bubble would be kind of larger and lifetime could be longer. So is it possible that the paramagnetic effect could also be enhanced? This is proposed by some theory people, but we can keep in mind that it could be one of the explanations. Also, other people propose that as larger magnetic field, the chiral symmetry breaking is splitted from deconfinement. So when people talk about the deconfinement of quarks, we always think that it happens at the same time as the chiral symmetry. But it turns out that if we have a large enough magnetic field, those two data points they could breaking at different magnetic field, at different temperature. Okay, I will summarize here. The search for CME is when we try to prove intrinsic properties of QCD in the non-predictive region. And then the STAR latest CME searches, it utilize an eventually selection method to effectively suppress the flow-related background. At 200 GeV, we predict an upper limit of 10%. And then at each of the 11, 14, 19 GeV, we observe a 3 sigma positive significance for charge separation. Altogether, if we combine, it's over 5 sigma significance. Also around 7 GeV, the lower end, it approaches 0 with a slightly larger curve. And we do need more theoretical insights. For example, if there can be the explanations for the remaining magnetic field, and there can be studies on chiral symmetry breaking or QGP disappearance around 7 GeV, or the chance of CME occurrence is enhanced near the critical point region. So thank you. These are two photos. One is our STAR collaboration meeting. Some of you might see yourself here. And then this is a photo I take on my graduate ceremony with my supervisor, Hong Kong. Thank you.
Okay, we have time for questions. Yeah.
Could you go back to slide 24, 25? It was sort of where you started laying out the different scenarios. The A, B, C, D, sorry, never mind, it was not, yeah. Do you mind going over these again? I kind of got lost in what we were.
Technical data, people are always very interested in. So the idea is single cube, paired cube. And then the difference is what kind of particle we use in the equation. So this is the definition here. And we are using the azimuthal angle phi r. If it comes from finite single particle, we call it a single cube. If it comes from a pair particle, you just combine the azimuthal angle phi 1 and phi 2, we call it phi r. Then we call it pair cube. So that's the definition. And then for single V2 is I probably have the definition in very early pages. You just replace that angle from a single particle to a pair particle. And that's the pair V2. So we do this because we think the major background comes from the resonance decay. And you really want something that can mimic the decay process. That is why we introduced the pair cube. So if you are using the mixed combinations, both the pair information and the single information will be included. Of course, this pair is it contains the true resonance and but they are diluted with the background from single. So by using the mixed results, by using a mixed combination, we think it can help us to capture both the single, in other words, both the CME background charge separation as well as the flow related charge separation. So that is why we introduce this mixed combination. Yes.
Maybe a related question. I guess, am I correct in reading that your plots later indicate that the C option is the best one?
Yes, that's right.
Do you have an explanation for why the D, the other mixing choice, doesn't work as well?
Actually, it's in our paper. The very fast explanation is when you measure this pair V2, it contains delta gamma. So in other words, you have a correlation between y and x axis, and this immediately leads to the oversubtraction. Also, since pair contains delta gamma, it means pair is sensitive to the CME.
So I have a more conceptual question. So can you go back to slide 12? Can you just go over this again?
Oh, okay, no problem. So everything starts when we have a local bubble where we have non-zero like left, like what we call mu5, or the difference between left and right hand particles, number of different. For example, here I draw more right-handed quarks than left-handed quarks, and then U quark and E quark here. So why do they like travel this way? The blue arrow here is the spin, and as soon as we turn on the magnetic field, the spin will align with the magnetic field. And if it's depending on positive or negative, it will either align or anti-align with the magnetic field. That part you can understand, right? So after the spin align with that, because it has a right-hand side or left-hand side, it also has momentum, and momentum is either aligned or anti-aligned with the spin. So it will go up and go down and then create a charge separation. Yes.
So J is current.
Yeah, J is the charge separation. It's also orange because it's created by this particle that carry momentum. Yes.
You know that there's, no, it's the same, maybe go on, sorry.
And so this J, I thought it's angular momentum, but it's not.
Okay, it's current.
Oh, okay.
It's electric current.
But it is orange, which is also the color for moment.
Yes.
But that's different.
So the story happens when you have, for example, the U quark, when you have equivalent number of left and right hand side, there is no charge separation because they cancels out, right? But when you have like imbalance for left and right hand particles, they will not cancel out. So this charge separation is induced when the particles move up and particles move down. So this charge separation was induced later on.
You mean imbalance for each species?
Imbalance between left and the right hand.
But I guess if I count in this picture, oh, okay, so there are four right and 2 left.
Yes.
Okay.
So I don't want to complicate the thing, but if you also want to consider the anti-quarks, it will complicate the story. But basically, you are the U quark with right-handed. If it's anti-quark, it will behave like BL. So I don't want to complicate the stories.
But will that like add up to 0 in the end if you include anti-quark?
If there are equivalent number. Yeah.
Okay.
If there are same number for left and right, you're right. So it will average out to be 0. But if there are equivalent number, sorry, or imbalance between left and right, they will not add up because they will travel to the other.
But if you put anti-quarks in, you wouldn't cancel it out, even with if you have a parity violation. That was Yochi's question. Putting in the anti-quarks just makes it a little bit more complicated to look through, but you wouldn't. You end up with a net charge separation, equal numbers of quarks. I mean,
You have equal number of quark and anti-quark.
I think this is where Yochi was heading. Right? Like if she says, well, you oversimplified the cartoon and make it work. I don't think so.
No, so you can easily just flip those D quark to anti-U quark. And then this would be U bar R, this would be U bar L, U bar L. And then I have to mention that mu5 larger than 0 means more right-handed quark, but it means more left-handed anti. So that's why I don't want to include element. So it's a flip in the concept. Yeah. So if you replace BL to anti-quark U, anti-quark U, anti-quark U, you will see there are charge separation in the upper and lower. I know it's a little confusing.
Andrew had a question. Hey, can you go back to slide 22? So I think I got a little lost around here. Would you mind explaining again what
the blue points are and what the red points are, and why specifically the intercept is what we want to match to have a good estimation.
Okay, so the blue data points are delta gamma, in other words, the CME observable. And the red data points are called A1 squared, the fluctuation of our charge separation. In experiments, we cannot measure this directly, but instead what we can measure is this delta gamma observable. So in other words, we can compare our observable to the true signal inside the model to see if they matches. And the x-axis is our V2 or our flow background. If you go to 0, means you suppress the flow background for the 0 limit. That is why we want to subtract the intercept. So
Okay.
the subtracted intercept will means the charge separation measured at 0 background. That
Okay.
should be our signal.
Okay, I think that makes sense.
Any other questions? A few, but I'll ask you in our meeting.
Oh.
Okay, great. Let's thank Zhiwan again.